This is the second of our Saturday Engineering for Everyone seminar series. My name is Pawan Hanumolu, and I'm one of the faculty members in the Department of ECE. Just one line introduction to the seminar series. This is sponsored by the Department of ECE, but we really borrowed some of the ideas from our friends in the Department of Physics. Today we have Amy, I should really say Professor Amy Visa. She is an assistant professor in mechanical science engineering. She got her PhD in Maryland, and she spent some time in Stanford before fortunately coming here. Today she's going to talk about, as the title says, bird-inspired systems for improved flight. She tells me that everyone is encouraged to ask questions at any given time, and especially kids that are younger than 10 years old. That's right. So, and she has some cool demos, and with that, I will not bore you anymore and leave it to Amy.
Awesome. Thank you so much. Can you guys hear me okay in the back? All right. So my name is Amy, and I'm super excited to talk to you about what I'm passionate about, which are birds. I love birds. I love how they fly. Ask me questions. Sometimes I won't know enough about birds to answer them, but that's cool. Then I can go and learn.
You belong to the Audubon Society?
The Audubon? No, I don't. All right. I apologize. Well, that out of the way. The talk is going to be great after that. But please ask questions. I can't talk for an hour. You'll talk to me. Let's have a discussion about things that excite you, things that you have questions about. All right, let's get going. So a little bit about the lab. We're called the Bio-Inspired Adaptive Morphology Lab, or the BAM Lab. And our vision and our mission is to actually create a space where we can do interdisciplinary research, meaning people from different disciplines can come together and work. So we collaborate with biologists and physiologists and material scientists, and we bring expertise in dynamics, but then we can go with other engineers that do other things. The work that we do is hard, it's exciting, but it's only possible because of my graduate students. They are awesome. Some of them are here, so I want to take some time to thank them for what they did to get this event ready. They were up until midnight working on stuff. So, all right, today I'm going to show you a motivation about why we need to talk about birds and airplanes in the same conversation. Then I'll share with you some of what I love the most about birds, and then some of our engineering adaptations from birds. And then I want to talk to you about where I see tomorrow, at least for the BAM Lab. All right? So this report came in 2016. First of all, question. Under 15, don't answer. Do you know what UAVs stand for? Above 15, don't answer. I lied. If you're under 15, you're allowed to answer. Go ahead. All right, my throwing game is really awful, so we'll see what happens. See, awful, like I said. Well, yeah. Anyway, so this market study came out saying that unmanned air vehicles, or vehicles, airplanes that don't have pilots in them, are actually projected for growth from, we're here right now, so extreme growth. And they're not talking about military, they're not talking about things that maybe we won't see, they're talking about things in our life. Entertainment, real estate, delivery, scientific research like us. So it's exciting. We're working on something that's relevant. And there's a ton of UAVs, and I will not be talking about all of them. They're classified mainly by size. They vary from a couple centimeters. Actually, some of them are actually only a couple millimeters big, and then to ones that might fill this whole room or bigger. I'm going to talk about mini UAVs or small UAVs because I think these will be the most relevant to a lot of the applications that were mentioned in the last slide. All right, but we have a problem. The problem is we design those small handheld UAVs the same way we design those huge ones. And there's a problem because the physics is not the same. And then I'm going to show you my one equation, but that means it's the one thing I would love for you to remember. This is called Reynolds number. It's a non-dimensional quantity, meaning it's a number that doesn't have a unit. And if you look at it, it's the ratio of things like density, length, and velocity, and viscosity. So we're in air, so let's not worry about density and viscosity. So that means it's a function of how big things are and how fast they're flying. So if you're small and slow, like these guys, you have a low Reynolds number. Let's say 100,000. And low is relative. I have friends in the audience that work on things much lower. But low for me is 100,000. Or you can think about things that big, and they're in the 1 million range. So you might think, well, what's the big deal? Let's take a look. All right, this is quick. If you have an airplane, there's 4 main forces in play. Lift to keep it flying, its weight, and then thrust to move it forward, and that thrust has to resist drag. So when Reynolds number decrease, 2 things happen. So this is lift versus angle of attack. An angle of attack, you can think of it as simply just how pitched the airplane. If the wind is coming straight at it, what's that angle? All right? So you'll see that for low Reynolds number flight, the lift is severely reduced. All right? That's the first hit. Are you ready for the second? To produce the same amount of lift, man, you got to pay a ton more drag. So then you need to power it more. But then you're lighter, so you can't carry a lot. So you see how it's the problem is kind of like a snowball that's rolling. It keeps getting bigger and bigger. So then my question, and what got me really excited, well, how can we design UAVs that are efficient and agile? And by that, I mean one UAV that you can send it out, a small UAV that you can send it out, and it can take off, land, hover, cruise, okay? And as any one of you would do, I turn to the experts. All right? So I want you to check this out. Just enjoy, fall in love. Birds are remarkable. They can land on a branch. They can take off from water. No matter how their size changes, their wing kinematics are nice and complex that allows them to do all these things. They fly individually, in groups. They fly very close to the earth, very close to the ground, or right by the surface of the water. They fly when it's nice and calm outside, or when it's gusty and we all don't want to leave the house. And all that because of their wing kinematics. So I got really interested in looking into their wing kinematics. So I want to take you now on a journey about birds. And this is a lie. It's not all about birds. It's a little about birds. And let's keep talking. All right, so here we go. We're going to play a game. All right, and you're going to, don't dry me, don't leave me hanging. I'm going to say wing, and you're going to say adaptive structure. Ready? Are you ready for this? Wing.
Adaptive structure.
Guys, you just ate breakfast. Let's do it again. Wing.
Adaptive structure.
You got it. When we build our wings, here's how I feel about them, and feel free to disagree. We build an airplane, we slap a wing on it, we slap an engine, and we send it. And the wing's allowed to move a little bit, but that's about it. Birds are not like that. Their wing, they feel and respond, and so they have, just like us, fine and gross motor controls. You can see a bird doing really minute changes with its feathers or huge changes, like in that video. The other thing they have, like us, how many people have been to the doctor recently? Good. Oh, sorry. Well, for just a checkup. But if you sit down, do you know that test where you sit hanging, your leg hanging on the side of the chair, and the doctor comes and kind of like hits your knees, some spot, and you almost kick him in the face? Yeah, that's reflexes, right? Also, if you're sitting and you're relaxed, your leg would swing back and forth. That's kind of your passive, how your body moves generally with no actuation. And then there is coordinated control. I need to go and reach out and get a glass of water. Birds have the same kind of controls. They have passive controls, where they just respond and feel without having to think. They have reflexive controls, and they have active controls. So for us to be able to build airplanes at that scale, we have to think about our gross motor skills, our fine motor skills, and then also passive and active ways of controlling how we move our wings. Birds have gaits. When we walk, you have a certain gait. When we run, I will not do that. The gait looks a lot different. Birds have that. When they're flying at slow speeds, this is during the upstroke, so when the wings are moving upwards. Sorry, that was loud. When the wings are moving upwards. So as the speed changes, their wing kinematics change. So they use gates, all right, just like us. All right. The other thing about birds that I want you to know, that there's not like a one-size-fits-all. Some birds are what they call specialists, all right? For example, swallows, they're designed for high speed. Albatross, soaring. This is a crow, and they're really agile. And this is an eagle, and they're high lift wings. So I'm not going to tell you the difference. You have to tell me the difference. What are some of the differences you notice?
The soaring wings are long and thin, like a glider's.
Yes, because they have to glide all the time. They have to stay, they're open, they're flying above water, so they have to have high endurance. Go ahead.
Compared to the eagle between the swallowtail, there's a high ratio of surface area.
Okay, yes. The eagle has much higher surface area, right? Why do you think that is?
So that way the eagle can have more lift.
Yes, because you guys, I'm sure everybody has seen, if not, homework. Go home, YouTube eagle getting a fish out of water. Has anybody seen that video beside me? Yeah, so they have to carry a lot of payload, so they need big wings. The other thing that I want you to notice is look at the wings of the albatross and the swallow compared to the crow and the eagle. You'll see there's a lot of devices, intricate devices. So an albatross, their wing is just nice, streamlined, long, and they're very efficient. But if you look at the eagle or the crow, there's wing slots, there's a thumb. It looks like a thumb sticking out, right? So now another question. Here you go. You're Amy, and you need to design an airplane that is, that can do a lot of things. You can take off, land, hover, cruise, carry payload. Which type of wing do you think we'd be most interested in? The eagles? I agree. It's like you were with me. Yes. Yes, that's the one. So in this talk, I'm really interested in high lift wings because these wings have have mission requirements that are very similar to UAVs that we want to design. So now, let's take a little dive, more like a snorkel into bird wings. Bird wings are like ours. They have an arm and a hand. Okay, the ratio is a little bit different, but they have an arm and a hand. And then the alula kind of sticks like a thumb, which if you think about it, is between our arm and our hand. They have also joints. So here we go. There's a shoulder joint, there's an elbow joint, and then there's a wrist joint. They have two huge muscles in their bodies, and those muscles are mainly used to flap the wings up and down. Because by the way, if you look at the power produced, birds have the most powerful muscle density, power density, because flight is so expensive. It's hard work. And then they have other smaller muscles and tendons and ligaments. So again, this is the hand wing and starts by the wrist, goes to the tip, and this is the arm wing. Now let's talk about the feathers a little bit more, and all this will come together in a couple slides. So different feathers do different things, right? So they have feathers that are mainly just to contour and give the wing like a wing shape. Others that are mainly for flight. The ones that are mainly for flight are the primary and the secondary feathers. And a big question, remember how I told you earlier that birds have reflexive, passive, and coordinated control? Well, if you look at how the feathers are actually embedded, they're embedded in the skin using follicles. Think of our hair, right? And around those follicles, there is mechanoreceptors, basically pressure sensors. So as the feather moves, because it's flexible, it can actually sense the flow. So there's a huge area of research now. There's hundreds of feathers, and they all get information. How does the bird brain process it? It's not. I mean, it's a lot of information. So there's a lot of those hypotheses in research now that what portion of that information is useful, what portion of that information is not useful, and so on and so forth. So anyways, and if you look at the feathers, they're inserted in the follicles, and you don't have like one muscle per, you don't have like one tendon per feather. They're actually grouped. So they're kind of bundled. You can think of them as bundled. All right. So far, I have told you that birds have fine and gross motor control, and also our research do fine and gross research, motor control research. So the first type of research I want to talk to you about is feather-inspired deployable devices. These are things like little changes in the wing that you'll see. But we also work on vehicle scale research, so bird-inspired UAVs, total systems. Okay? And that's what the engineering, we're going to start the engineering piece of the talk now. Any questions about birds? Flight? Yes?
I think flapping wings is probably less efficient than propeller.
Okay?
Is that true? Because that would severe, even though the wing might be more efficient, if the power is less efficient, in the end, it's probably...
So this is like the million-dollar question in flapping wing research. And I'm going to answer it in the end of the talk, but the answer is it depends. And I'll tell you what it depends on. But stay tuned and let me know at the end if it makes sense. Okay? Cool. Sorry. The question, I'm sorry, I should do this. The question is if the way the wings are actuated are inefficient compared to propellers, then even though the wing design might be exactly what you want, why would you go for a flapping wing UAV? Because then it becomes inefficient because it's power hungry. Sorry, go ahead, question.
We were kind of curious about how birds' wings with feathers are different than maybe dinosaur wings or bat wings with more of a membrane.
All right, bat wings are crazy. They're awesome. So if you look at insects versus birds versus bats, I don't know a lot about dinosaurs, but I'm going to go insects, bats, and birds. Insects, actually, their wings are completely passive. There's nothing. Like, think of it, the wing is made, and then it kind of gets put on the insect body, and then there's a muscle in the thorax, and that's where all the control is. The wing has no actuation power on its own. If you look at birds, they're the next step up. There's about 45 muscles, and there's the feathers, and they deploy because of the passive. Now, if you look at bats, they have hundreds of muscles, and it's all in this thin membrane, and their kinematics is great. So bats, on the level of crazy, bats are the craziest. Yeah. Any more questions? All right. You guys ask good questions. Keep them coming. All right. So let's talk about feather-inspired deployable devices. The first system I want to talk about is the coverts, and the covert feathers are they're contour feathers. So they cover the whole wing. They actually make the most type of feather, the most dominant type of feathers. And they have passive and active deployment behavior. And people have done research on bird wings to say that different coverts react differently in different flight conditions based on their location. Okay? So, and here we have a mock-up of the coverts that are very simplified just to show you where they would be. And we'll talk more about this demo in a sec. So if you look at an owl, for example, you'll see they have coverts on the top surface of the wing and the bottom surface of the wing. And you'll see them deployed what I call complex maneuvers. What I mean by complex maneuvers is very high angle of attack, low speed, and where stall is a problem. And stall is when airplanes can't produce lift anymore. All right? So here's a video of an owl and a macaw. And the macaw is flying at high angles of attack, and there is gust, and you see the owls, the covert deploying. Here, the owl is going on a perch, so very high angle of attack, like 45 degrees. And you'll see as it comes to approach all the lower coverts. Now, I want your intuition, because our intuition works great. Do you think this is passive, like something that just happens because of the flexibility of the feathers, or you think it's active? How about that? We're going to do, this is democracy. All right, raise your hand if you think it's active. All right, raise your hand if you think it's passive. All right, the answer is nobody knows yet. All right, there's actually a lot of research going on. There's a lot of hypotheses about, when you see a more coordinated deployment, then that's active. But, when you see little ones pop up, that's because they're flexible and there's a phenomena called flow reversal. That basically air is going the other way and it pushes them up. So stay tuned. Okay. So now as an engineer, I want to design and implement a covert-inspired flap system or deployable structure because I want to improve lift production during those complex maneuvers where I'm really pitched up. Because if I take, here, let's do this. Let's take a Boeing 747, shrink it down so that's the size of shadow here, and then I go to high angles of attack. Do you remember that Reynolds number, green and red line? I would fall out of the sky, no question. Okay? So, so that's what I want to do. I want to be able to, use the coverts so that I can do this high angle of attack maneuvers and not fall out of the sky. So where do you begin? And I think this is where you guys kind of want you to give you a glance of how do you start from biology and go to engineering, and tell me how you feel about it. And because I want to hear what your response, because I've been doing, when you're doing something for a long time, you're kind of in your lane. So I want to see how you guys react, and everybody's allowed to react. But anyway, so we said, okay, maybe what we need is to get a wing and cover it with a bunch of flaps like this. And then we'll ask ourselves, we'll use wind tunnel experiments, and we'll ask ourselves, how many flaps should we put? Where should we put the flaps? How flexible should those flaps are? And then we had like parameter overload, right? There's hundreds and thousands of parameters that you'd have to think about. So like I say in my lab, I say KISS. Keep it short and simple, all right? Let's keep, it's not, the other one, we don't use names in my lab. KISS, all right? So we said, all right, let's build an airfoil with a single flap, rigid flap. Let's put it in the wind tunnel, and let's try to understand what's going on. Here's actually a video of the flap. So you're looking, this is the back. This is the trailing edge of the wing. And you'll see the flap deploying and vibrating in the wind tunnel. And actually, in the experiment, you maybe probably can't see it, but the wing is being pitched up and up. Like the angle of attack is increased incrementally. And you see those vibrations, right? And then at some point, I don't know if I trimmed it or not, but at some point when we pitch it way up, you'll see that the flap completely flips over because it has no stiffness at the hinge. We just kind of taped it on there. All right. So here we go. This is our experiment, the airfoil with one flap, and we change angle of attack. So this is this figure. Let's change angle of attack. Let's pitch the wing up, and let's measure lift, or lift coefficient, and let's vary beta, which is how open is the flap. We controlled, this experiment we didn't control the angle. In other experiments that we did, we actually varied the angle gradually. All right. Tell me what you see. What are some of the things you see? If you're me and you're looking at this, is this good or is this bad?
It looks good because, like, the normal, it has better performance than the normal airfoil I've seen.
First of all, kudos that you figured out which one is the normal, because I did not say it. So good job.
It says baseline airfoil.
I know, but not anybody can figure that out. You got to give yourself props, man. All right. So this is the baseline, which is the wing with no flap on. And then this is when you change beta. So you're saying it's good, right? Do I have any counter arguments that this is bad? You're saying here, right? Can you speak up? So, two things. Here, at low angles of attack, the flap hurts all the time. And that makes sense, right? It's almost like you kind of, now it acts more like a spoiler, right? And then, but what's exciting is the flap is able to improve the performance here, which is the area where the most lift is being produced, but also the stall behavior is better. And then we actually have other tests that I didn't show here because we have tons of data where you'll see that the wing stalls later. So the first thing we notice is exactly what you guys said, is lift is improved here. But what that means is we need some kind of stiff hinge that doesn't open until when you're ready for it to open, right? So at low angles of attack, when we're flying nice and level and steady, everything is closed. And once we go to high angles of attack, then those things open, just like the owls did, right? But then You know, it's like, why? We always ask the question, why? What's the physics? Why does it work? So we did some simulations. And let's talk about this because it doesn't have a lot of labels because I didn't want to, I wanted to keep things simple. But the redder it is, the faster the speed. So here would be as if there's nothing in the flow. This is the velocity, the airflow before it hits the wing. The blue parts, that means there is a velocity deficit, meaning slower velocities. And the bluer it is, the worse, because it's called a deficit. And that deficit, you can actually relate it to drag. So now, here is, look at the blue area without the flap and with the flap. What do you notice? You think it's smaller?
With the flap, it's smaller on the back,
Mm-hmm.
but it's bigger under the wing.
Bigger under the wing? Oh, you mean here?
Yeah.
Okay. Actually, that's a great observation. We actually looked, and what the flap does is create a pressure dam, meaning, and it creates a pressure dam, meaning there's okay, let's all pretend we're an air fluid. We're an air particle, all right? And we're kind of running on the airfoil surface. At some point, friction becomes too much that you have a very hard slope for the pressure to climb, right? You're going from a nice low pressure to a high pressure, so it's almost like a lot of work. And we call that adverse pressure. And the flaps actually reduce that adverse pressure, reduce that slope. But what it does is then some of that effect gets mitigated forward. Okay? But anyways, the other thing, if you notice, and it's really hard to see here, that the blue area starts a little bit later in the wing's geometry. So then, okay, great. So now by putting just one simple flap that is rigid, we are able to kind of capture some of what owls do or eagles do when they deploy their coverts, to create dams so then the deficit is lower. So I wanted to show you a lot, so I'm going to go over this part a little quicker. But anyways, we were psyched. The technical term is psyched. We were psyched because you can create one structure that's so simple, adds very minimal weight, and we can do then this structure will help us improve our lift, the maximum lift we can produce, and then and it can delay when we fail, basically. And then we can make it adaptive. Actually, we did. One of my students is now designing a hinge so that it closed when we don't want it to open, and then it opens at a certain angle at the maximum CL range, and it opens at a higher angle at the other range. Just go ahead.
So you're saying that if you can change the angle of attack, it's better to have the flaps on top as opposed to a fixed wing where it's better to have it on bottom?
They're doing different things. So the flaps that you see on a Boeing airplane, that when you're landing and it kind of opens up, what it does, it increases camber, makes the wing more curvier, and that allows it to basically operate. It kind of takes that black line and shifts it up. The whole line gets shifted up, and you're increasing drag and a lot of things. For those flaps, they're doing different things. You're just going at a higher angles of attack, and what it allows you is to maintain lift production. So it's different. The physics the mission and where you deploy that flap is different. This flap versus that flap.
So you said that in the experiment you changed the angle of attack. Did that just mean you shifted the angle of the...
Could you repeat the question?
Sorry, the question was, what is the difference? I need to be better at that. What is the difference between the flap that you deploy? When you're landing from your airplane, you look out the window and you see a flap, a trailing edge flap deploy. What is the difference between that flap and the one that you put on top? And the answer was that they're different mechanisms. One of them is increasing the airfoil geometry so that you can produce more lift. The other one is changing the flow around the wing by creating a pressure dam so you can access spaces in the design that you could not have before. And then to answer your question, there is a motor right here that pitches the wing up little by little. Question?
I don't think it would work in here, but might there be a chance of you being able to actually apply that in this auditory?
We won't be able to fly it, but we will flap it. And I'll show you videos. I'll get there because it's exciting. All right. So another device that we looked at is the alula. And let's see if I can, I'll do this in a sec. But basically, it's a thumb. And the alula is attached at the leading edge. I don't know if you guys can see it a little bit here. It's attached at near the leading edge. And again, the alula gets deployed at really, really high angles of attack. Not like the coverts. These are way higher angle of attack. Way beyond after the airfoil would have stalled. And what it does is pretty incredible for being such a small device. High lift wings, all of them have very pronounced alula because of that, because then you can be highly maneuverable, like you see this owl. This is actually a video from the bottom of an owl approaching a prey. And then it allows them to do very low takeoff, it reduces the takeoff and landing distances, and then allows it to carry a lot of payload while it's doing all of that. So we wanted, right, this is now a question that's very relevant. Okay, here we go. This is how aircraft, if you go to the airport right now, this is how they do some of what the alula can do. But it requires hydraulics, and it's super complex. So now the question is, how do you do it for small UAVs? And we said, well, let's try something that looks like an alula. And then we took also an experimental approach to understand more about it. And I want to show you what we did. So we looked at literature of alula, which is spelled with A-E when it's plural. And we find out, okay, what's the right geometry for the alula? And you'll see it's very different. And we looked at bird cross-sections of what the alula looks like. And then where should we place it? We asked that question. What's the effect of changing the location? You know, and birds, they come the way they are. We asked the question, what happens if you change the way they're deflected? You know, is it sensitive to that? And we put it in the wind tunnel, and we did experiments, lots of experiments. And here's 3 things I want you to take away from that figure. First, that the alula improves lift during very complex maneuvers. Look at those angles of attack. This airfoil stalls at around, what, 10? 10. Okay? So this is way beyond where the wing would have been gone. There would no lift production whatsoever. The other thing I want you to notice is the location matters, right? And for different angles of attack, around mid-span, that's where most of the alula that makes a good effect. And that's actually very close to where birds also, some birds. And then the other thing I want you to notice is the alula angle has to be lower than the wing angle. So even though the wing might be pitched up this way, right, the alula angle has to be lower, right? So that angle beta has to be negative. Now look at the improvements, you guys. This is percent. 30% lift increase. That's 30% more of your weight that you could not have carried, now you can carry. With something that's not even, what's the percent, 15? 15%. 15% of the full wing. Okay? So, and then we did some flow visualization, and we found not only are you improving lift, those red regions are turbulence. Okay? That's the turbulence intensity, or the turbulence kinetic energy, to be more specific. With that, the alula, look how red it is, how intense it is. With the alula, almost all of the turbulence here is gone. Yes, you do pay a turbulence penalty because you basically added a wing that has its own flow, but that is noise reduction. This is drag reduction. And unlike the leading edge slats, which is the picture I showed earlier, we actually found a really cool effect that Mahari discovered that's pretty awesome, that says that there's a really cool interaction between what's happening at the tip of the alula and what's happening at the tip of the wing, and they interact constructively to prevent wings that would fail. Even if I added a leading edge slat with the alula, they won't fail. Okay? So a lot of these I mentioned already, right? Lift enhancements, the interaction between the alula and the wingtip. Morphology is important, but actually the morphology that we noticed in the experiment with those rigid alula sections, simplified sections, agree with a lot of the angles that we noticed in biology. And we could reduce drag and sound, noise effects during flight. All right, last wing, and then we'll start flapping, I promise. Last concept. Have you, remember when we looked at the eagle? Remember how slotted their wingtips were? Right? Unlike the albatross that was nice and pointy. Well, when you do that, everything in life is a trade-off. When they do that, they become more maneuverable. So they can fly in tight spaces between trees and things like that. What ends up happening is they're no longer elegant. They're stubby, short and stubby wings compared to the albatross. So they pay drag penalties. So nature has evolved those slots to say, flow. This is actually the technical thing that the feathers told the air. They're like, flow. We are not short, stubby wings. We're a bunch of really nice, long, pointed ones. Okay? So birds have evolved those wingtips to overcome their short, stubby penalty that they had to pay to be maneuverable. Okay? And the reason why those slots, like structurally wise, because if you look at a feather, and guys, this would be a really cool exercise. Try to find, go online, there's something called feather atlas. Look at the feathers of an albatross and look at the feather of an eagle. And you'll see how asymmetric, this is actually the Harris hawk, which is also with the high lift wing. But look at the Harris hawk, look at an albatross, and see how some feathers will be nice and symmetric, and then there'll be no slots. And other primary feathers will be nice and notched. Okay? All right, so if you look at those, and this is a very new project, so there's only like a couple slides, but I want you to get excited. So if you look at what those bird tips do, wingtips do, right? They have dihedral, so they kind of bent up like winglets. If you go to the, a lot of airplanes now have winglets, for very similar reasons, by the way. And then you also see them feathered, meaning like twisted down. And then you see them, the spacing between those things change. So those are the 3 degrees of freedom that we've noticed by looking at a lot of videos of wing tip flight. And we were the first to define these degrees of freedom that way. All right. So we said, well, how are we going to do this in an engineered system? Well, how about if we create a wingtip that can, vary spacing, vary twist, and also change dihedral. Okay, now, here we go. I only have like yay much of wing. Imagine if I had to add 3 motors, 3 controllers, 3 sensors. I'm going to be a brick. And actually, a lot of the research, the reason why Shadow is super cool, and I love her, is because we're one of the few research groups that actually fly the morphing mechanisms that we create, because we use a lot of passive techniques. Some labs that do active techniques, they're interested more in the controls and the sensors and actuators, but they end up being too heavy to fly. So we always keep that in perspective. So we said, and this is, when you do this, there's aerodynamic data that shows you increase lift, reduce drag, and kind of overcome this penalty of being a short, stubby, moderate aspect ratio wing. So our concept, which I think is cool, but again, I'm biased. All right, we're not going to do everything active. We're going to learn from birds that have passive and active control. So we're going to have a bistable, or let's say just a truss for now, right, that can open and close with very little force. And in this video, we have a small wire. It's called shape memory alloy. When you heat it, it shrinks. And we can just open and close the feather spacing. Okay? So that part, we're going to pay some power penalty. But we refused to put anything else active. So what we designed, and I want to show you this on the camcorder, the dock cam. Is a wingtip that when it bends because of lift, it also twists. I'm not twisting it. I'm just applying a load, a straight down load. So when I apply that load, I also twist it. That's called bending, torsion, coupling. And you do that when your material properties are not all symmetric. So here we are. We're flying, all right? We actively open up the slots. Then because these things are flexible, right? The air would make them bend upwards because of lift. And when they bend upwards, they also twist. So this is like shampoo, conditioner, and body wash, you guys, all right? So anyways, this is exciting. We've built proof of concept for everything. We have not integrated and flown it yet, but we will. And we're super excited about it. All right. Now, shadow. Let's talk about shadow. So I talked to you about a lot of the fine motor control, like little changes, like whether you deploy a flap or stick your thumb up or open your wingtips, right? Birds also do gross motor control, like big changes. Now, going back to the question, and I forgot your name. What's your name? Jack. The question that Jack asked. Why don't we use these? Like, why flap at all, right? And I know that's different than the power efficiency question, but I'll get to that too. But why flap? We have already small drones that are fixed or rotary. The problem is, if you want those 3 sides of the triangle, those platforms only gets you 2 at most, but not all 3. What can get you all 3 at low Reynolds number? I'm not talking we should build our Boeings and Airbuses to flap. I'm talking about small scale, right? Yeah, if there's a flapping Boeing, don't go in there. You're probably going to throw up, all right? And don't blame that on me, all right? I'm talking about small. All right, so to get those 3 sides of the triangle, meaning to be small and slow and stay efficient, to be able to do all these different missions and to maintain your agility, flapping flight gives you that. And the reason why is because of the way they produce lift. They exploit physics that neither platforms exploit. Things like cold circulatory and non-circulatory lift effects. And we can talk about that probably over a glass of wine, all right? All right, so okay, but come on, I don't want to be a salesperson. You can't just flap and be it. Like when I flap shadow right now, you'll see the wings just go up and down, and that's not enough. You need to articulate your wing, meaning you need to morph, just like you saw the first video when they were moving. All right, one of my favorite college professors at Penn State when I was an undergrad he's like one of those, old airplane designer people that had just amazing presence. And he said, all right, if you're designing an airplane, when you're done, it shouldn't weigh any heavier, it shouldn't cost any more, and it shouldn't use any more power. What? So, of course, that's an exaggeration, but the idea is you can't just add stuff, keep adding like linkages and mechanisms and actuators and sensors, because by the time you're done, you won't be able to fly. So for my PhD, I got really interested in the idea, how can I articulate my wing, but add very minimum weight, no power expenditure, and very minimal complexity or cost? And the answer for that, and this was me confused for 4 years, but anyways, the answer for that is passive morphing, okay? What does passive morphing mean? Meaning create a structural modification, put it in the wing, and let it interact with the flow. Another technical term is fluid structure interaction. Exploit things like fluid structure interaction to get the articulation you want. So that's exactly what we did. This was a 4-inch piece of plastic that we inserted in the wing leading edge and to mimic the function of a wrist, an avian wrist, and I'll tell you more about it. And we flew. And I want to share with you some of those results. So we looked, when you are a PhD student or any student that works with things that are alive, you start giving them names, all right? So this is Charlene the cockatiel. I'm not sure her name is Charlene, but that's what you do, just like this is Shadow. So me and Charlene spent quality time, weeks of me looking at her flying and looking at, the kind of kinematics she uses at different speeds. To be honest, I don't even know if it's a she, right? But anyways, so what I notice is during the upstroke, the wings are fully extended. And that makes a lot of sense, right? Because if you kind of imagine that you're in the car, stick your hand out, right? Push down. What do you feel in your hands? Up, right? Positive lift, right? If you now do the same, what do you feel in your hand? Negative, right? So when in the downstroke, the wings are fully extended because you want the most paddle. I know I look ridiculous, but that's what happens when you work with birds. Anyways, so you need the biggest paddle. And then on the upstroke, you see the wings kind of get tucked in. You see them bend, sweep, and twist. So I said, I'm just going to look at the bending. And we worked with Penn State. I was at Maryland at the time and worked at Penn State. And we designed this compliant hinge. And if you can see here, the hinge is allowed to bend. So as the wings are moving up, the hinge is allowed to open. And as the wings are moving down, it locks. Can you see that? All right. If you can't, well, watch these videos. There's no joint here. There's a joint there. And we designed that joint actually using geometric properties to get bending and some sweep too. Here's a snapshot at mid-downstroke and at mid-upstroke. And you'll see that the wings have very similar kinematics. So as we're pushing down, the wings are fully extended. And then as we go up, the wings kind of get tucked in. This is just a torsional spring with a lock. That's exactly what it is, right? You guys, I'm sure, have played some of those things where you can bend it down, but when you let it go, it doesn't go up because there's a lock. You can buy these, bending torsional springs with locks. And we did experiments on the bench top first. So we flapped it on a stand. And solid meaning no joint, compliant means there's a joint. And look at the power consumed. We reduced it significantly. All right, look at the net lift. Now, here, this is, don't look, look at me. All right, here, I'm a wing, fully extended, all right? I'm gonna flap up and down, up and down, up and down. How much force am I producing? In this direction, up and down, up and down. Yes, that was supposed to be a trick question. You guys are so good. Yes, because the amount of positive lift I produce this way, I cancel it out this way. So when you take the mean, that's exactly what's happening here. All these blue dots are about 0, which is the wing that up and down symmetric. When we added the spine or the joint, we're able to improve lift. We're able to carry about 20% of our weight just by adding an additional 20% of our weight, just by adding this hinge, just by articulating our wings. And we were able to do that by maintaining, and we maintained our thrust, so we can produce the same thrust. And that's a big deal because if you think about it, if your paddle is broken, you might, birds use their wings to produce both lift and thrust, right? So we were able to show that even though we're able to bend, we can maintain our thrust, which is a big deal at the time. Anyways, but where was the test? Was it a real flight test? Or we were clamped on a bench? Clamped on a bench, right? So another terminology in aircraft design, anything that you add to the aircraft has to buy its way on. Like if you talk to big wigs in industry about aircraft design, anything that you add has to buy its way on the aircraft. So the question is, did the compliant mechanism or this joint buy its way in this aircraft? When it doesn't have to carry the additional weight, because we added some weight, it seemed like it was a great idea. So then we had to take it somewhere where we actually can fly. So we went to Wright Pat Air Force Base. They have this awesome facility where there's like 60 Vicon cameras. Anybody watch Avatar? All right. So we equipped the wing with motion tracking dots. We went to Wright Pat Air Force Base, and then we flew. That was me back in the day. This is not a real flight. This is a slow flight, just to show you guys. And we were hanging from a tether, but then we would take off and it would be actual free flight. And when we did this, this was data. This was the first set of data. And we're not old. This was only like maybe, 5 years, 6 years ago. And this was the first set of flapping free flight data from a flying unmanned vehicle. That much data. And we showed that we do lose the power advantage, but we even it out. So we get we did buy our way on the ornithopter because we improved lift, maintained thrust, and didn't spend any more power. So it doesn't look any different. It doesn't weigh much different. It didn't cost us any more power. And that's because we implemented bird-inspired articulation techniques, passive wing morphing. All right, now, before I do this, I think it's time to flap shadow. Don't you agree? Now, I need volunteers. All right, 1, 2, 3, 4. Come on down to Bordentown. All right. Okay. Who has hair that actually moves? Mine doesn't. Do we have any girl in science or not in science volunteers? Girl who wish to be in science volunteers? Jack, how much does your hair move? Let's find out. Let's find out. All right. So why don't you hold shadow?
Okay.
Here, you'll stand behind shadow. You'll be in my hair demo for, and then we'll switch. All right. Okay. So you need 2 hands. One here away from the gears. All right, and one here. All right. All right. Shadow is no joke, so hold tight. Okay? Are you ready?
Yep.
All right. So this is just telling me, okay, so first of all, I want to show you some of the controls, right? We can yaw, so that allows us to turn. We can pitch, and then when you couple it, you can bank. Now, shadow flaps, so it produces lift and thrust using the wings. So lift, you'll notice it. What's your name?
Blake.
Blake. You'll see that Blake's hand, I'm sure he's strong, but you'll notice that he might start feeling some force. So he'll tell us, make it seem like it's really hard, okay? And then look at Jack's hair, theoretically, and it will move, all right? So here, this is our demo for lift and thrust. Very technical, you guys. All right. Look at his, actually Blake's hair is moving because he's closer. Get closer, a little closer. Here we go. All right. All right, let's switch. Who wants to hold shadow?
I will.
All right, let's take turns. Here we go. All right, here we go. One here, one there. All right.
I want to see how much lift it actually.
Yes. Blake, how did it feel? Did it feel like it was trying to pull up?
It felt like it was going to go pretty far.
Yeah, nice. All right. Look at his hand. This is the perfect demo. That's why don't go on a Boeing that's flapping. You throw up. All right? Okay. All right. Next. Who wants to hold it? All right. You guys take turns.
I'll do it.
All right. Perfect. Can you turn to the audience so they can see it too? Other way around. Other way around. Face them. Yes. Okay. All right.
Go.
You're good?
Yeah, I'm good.
Okay. I would lift it up a little bit above your head. Yeah.
Oh, no, I think he would get in the air, but it's...
Uh-oh.
What just happened?
The spar went out. That's what happened. That's what happens when you have a demo. That's exactly.
Did it break it?
No, didn't. It just went out. Yes, dislocate his shoulder. Mild shoulder dislocation. All right, we'll give it to Mahari, the bird doctor. Can you fix it, Mahari? Anyways, sorry. When we fix it, I think it's fixable. All right. Thank you, guys. Have a seat.
You're welcome.
All right. So now this is kind of more of I didn't spend a lot of time on that philosophy about what's next because I want to hear what your reactions. We have a little bit of time. So, I showed you some feather-inspired deployable devices. I showed you passive morphing is possible and effective. This is, some proof of concept that we can do in engineering fine and gross motor control. We can do active and passive control. We can also, I didn't show any coordinated controls, but this is something that we're definitely looking into. The thing I want to show you is I showed you a lot that biology give us the inspiration, but we're now at the stage because we've created nice, robust experiments, of course after Shadow broke, but anyways, nice, robust experiments where we're now actually writing papers and publications that informs biology. Because we can change things in the wind tunnel easy, and we don't have to train the bird or feed it, or so we're showing and practicing. We're showing them some cool physics, explaining some physics that are very relevant to bird flight. I think, and this is again very biased. I love the work we do. It's interdisciplinary. We get to talk to people. We learn things all the time. We work in challenging things, but I think it's really cool because we get to create really nice tools. And if you ask me what are we doing tomorrow, I'll tell you that we started already, what we're doing tomorrow. And this next slide is like death by videos. But here is a concept of an aircraft that we're trying to develop that has the 3 feather components that I showed you. This is Mahari here, flying Shadow, actually at University of Illinois. This space is way too small for Shadow. So we now fly out in the armory once a month. This is an origami robot that Ayuna is working on with Kim, who's somewhere. And they are using origami to create a crawling robot. And then this is a project we're working very closely with entomologists on click beetles because if you saw in the beginning of the video, actually you'll see it now, those beetles can click their body and jump tens of times their body length in the air, and you'll see it now. So we're continuing this interdisciplinary approach. We're excited to see that once we learn the physics, the adaptation doesn't have to be a complete mimic. I think that's something that was a big thing. A lot of the things were simplified and rigid, but the physics, as long as you can copy the core principles, you don't have to put feathers on an actual airplane to make it efficient as birds.
Would you consider Shadow on the lines of biomimicry?
Shadow right now is a very nice research platform where we can add things and test what happens. I think Shadow has, and it's good kind of to show people and like that, but the next step is actually to turn Shadow into something like this. And we have some tests planned for the summer where we're going to put the alula on a fixed wing and then on Shadow. So now to get to the last thing, to get to Jack's question, a lot of those things are applicable to fixed wing too, so that's without flapping. But the question you want to ask yourself for propulsive efficiency is, you also have, you're right, in nature, flight is very power consuming. And you might argue that propellers are more efficient. But we've had a lot of years experience building propellers. We have not spent nearly as much time learning how to create efficient flapping mechanisms. So I think we can. And there is ways that you don't have to power the whole stroke, for example. And we don't have to copy the muscle requirements of birds. So, yeah. All right. Thank you guys so much. If you have any questions, please feel free to ask. We'll be hanging outside. We have stickers, pens, more candy, and this demo that has kind of representation of everything I talked about that you can hold and touch and play with. All right, thanks. Appreciate it. You guys are awesome.